Hi, my name is Veno and welcome to my talk about Lévy processes on a manifold with a connection. What I'll be presenting today is joint work together with Alexander Mijatovic, and we both come from University of Warwick and the Alan Turing Institute. Okay, so let's first start with the classical definition of Lévy processes. So those are exactly stochastic processes on the Euclidean space, which have independent and stationary increments. Alternatively, these are exactly time homogeneous Markov processes which are also space homogeneous. So such a definition can be quite easily generalized to Lie groups or any other topological groups for that matter. All we have to do is we need to change the Euclidean increment to a group increment. But the question naturally arises, what can we do when our state space does not have a notion of an increment? An alternative approach was given by Applebaum and Strad, and they were able to define isotropic Lévy processes on Riemannian manifolds. But there was still a gap left open. For example, if you consider a torus as a Riemannian manifold, then the isotropic Lévy processes on it form a strictly smaller class than if we considered all Lévy processes given by the Lie group structure. So our goal is to provide a suitable generalization of this, and we are thus led to consider Lévy processes on a manifold with a connection. So let's first talk briefly about the geometrical intuition behind the construction. So this is what we use is development of curves from differential geometry. So what we do is we start with a curve on the tangent space. So this is this curve on the tangent space. Tangent space is simply a Euclidean space of the same dimension as the manifold. And then we sort of roll the tangent space along the manifold so that the point of contact is always our curve from the tangent space, and then we get this another curve on the manifold, the developed curve. So this is also known as a rolling without slipping, and to do it rigorously, we first notice that actually the tangent spaces change, and we need to somehow identify them with one another, and this is given by a connection, which sort of this additional structure which connects different tangent spaces. Okay, so what do we want to do then for processes? Well, we would like to just start with a process on the Euclidean space and somehow develop it. It turns out that it's actually easier to do an intermediate step, which is considering a frame bundle, just like a large manifold, and it's sort of above the base manifold. And then the connection induces these fundamental horizontal vector fields on this frame bundle. And we can then consider horizontal processes, which are a solution of a particular stochastic differential equation given by this horizontal vector fields and the suitable integrator, and then look at the projection of the horizontal process to the manifold. So this construction, for example, if we look at it on the Riemannian manifold, we take the Lévy-Civita connection, yields exactly this celebrated Elworthy-Malявin construction of Brownian motion. What they do is they simply have to take as an integrator classical Euclidean Brownian motion. So what we want to do is swap around the integrator and take as an integrator a Euclidean Lévy process. There are two issues here. So first, we need to consider a suitable stochastic differential equation, and we're going to talk about this later in the talk. And another issue is that we need to ensure that our projection remains a Markov process. To sort of illustrate the issue, we know that we have these different tangent spaces, and we need a connection to identify them with one another. But, for example, this identification sort of depends on the underlying curve or the underlying process. And once we come to the same point again, to the same tangent space, this identification might not be identity anymore. For example, here on this figure, we can start with this blue vector, which is sort of then moved along this loop in the clockwise direction. And once it comes back to the same tangent space, it's actually a different, this red vector. And this is quite common. And so we would also say that this blue vector has been parallelly transported. And parallel transport typically is not identity, and this failure of parallel transport to be identity is captured by the holonomy group of the connection. So what it turns out is that in order to get a projection which is Markov process, we need to require that our Lévy integrator is invariant by every element of the holonomy group. So this is our requirement. And also, we can see that this kind of requirement is sort of the basic requirement that we need to have to get a Markov projection, and it's typically less restrictive than the isotropy requirement from this article from Applebaum and Strad, because isotropy means that you have to be invariant by all elements of the orthogonal group. So now we can actually state our definition. So we start with the manifold M, and we actually need to consider a holonomy bundle, which is just a sub-bundle, a sub-manifold of the full frame bundle, and it has the associated holonomy group. Then we consider a Euclidean Lévy process, which is holonomy group invariant, and we have this horizontal Lévy process, which is a solution to Markov stochastic differential equation. And then the projected process X is a Markov process, which we call a Lévy process on manifold M. From this definition, it seems that there could be some dependence on the choice of the holonomy bundle and the holonomy group, but actually the holonomy bundles are all diffeomorphic with one another, and the holonomy groups are conjugate with one another. So it's not surprising that it turns out that the class of Lévy processes does not depend on this choice of the holonomy bundle, and this is all summarized in our theorem. Okay, so why is this definition a suitable generalization? So first of all, it's quite easy to see that it is that isotropic Lévy processes are simply a subclass of our Lévy processes, but also we could, on a Lie group, we could consider a flat left invariant connection, and then we would get exactly classical Lie group Lévy processes. And the similar kinds of considerations could also be done, let's say, on homogeneous spaces, which are quotients of Lie groups. So now we finally reach the point where we need to discuss this special stochastic differential equation. So because our integrator and the solutions have jumps and we are on the manifold, we need a particular kind of stochastic differential equation known as Markov stochastic differential equation, or the canonical equation. And so how this is done is we start with certain vector fields on the manifold. We have our semi-martingale integrator, and then we can describe what actually it means for a process to be a solution. I'm not going to go into all details, but basically it has two parts. One part is this Tratonovich integral here, which is for the continuous part, and then we have this countable sum, which looks quite unwieldy, but it actually is easy to understand it intuitively. So what it tells us is that when the integrator jumps, so does the solution. And how do we get the endpoint of the jump of the solution? Well, we combine the jump of the integrator with the vector fields to get a single vector field, and then we flow along that vector field for a unit time, starting from the start point of the jump, and the end point is then obviously the end point of the jump. And so this exponential here means this flow exponential, meaning flowing for a unit time. So to illustrate this a bit more, we have this figure here. So we can think of, so we have this our integrator here, and then so while it's moving continuously, so is the solution. And then when it makes this straight jump, so what happens with the solution? Well, the solution also jumps and is given by this well, not a straight jump, but this is not manifested. So we just move along this flow equation. So we solve this flow equation to find an endpoint. And then again, we move continuously, and then we have another jump and so on. So now, for the final part of the talk, I would like to discuss generators of Lévy processes on manifold. First of all, it's quite easy to compute generator of horizontal Lévy processes, so the solutions to the Marcus ASDE. And then, since we are looking at a projection, we expect that the generator of the projection is simply the push forward of the original generator. And this is indeed the case. We have the following theorem, which gives us exactly exactly the form of the generator. Here, these parameters A, nu, and B are just the generating triplet of the Lévy integrator. And we also have the converse result. So if we start with the process X on manifold, which has this as its generator, then it is exactly Lévy process on manifold as per our definition. Now I'll talk briefly about what is needed to prove this characterization, this theorem. And so we essentially need to construct our integrator just from the solution X itself, so process X itself. And this is, so we need to construct the so-called stochastic anti-development, and it needs to be a Euclidean Lévy process. So unlike a continuous case or smooth case where we have a nice correspondence between the solution and the anti-development, jumps pose some difficulties, and this is mainly due to the fact that the exponential map might not be injective, which means that several jumps of the integrator could correspond to the same jump of the solution, and vice versa. One jump of the solution does not uniquely determine the jump of the integrator. And so we need to sort of extend our probability space and suitably construct our integrator, our stochastic anti-development. We can do this. We have our technical results which show that this can actually be done, and we actually be able to construct this for general discontinuous same martingales, and thus generalizing these earlier results from Pontier and Estrade, where they actually require quite strict condition on the manifold and the connection. Okay, so thank you for listening to my talk. And before I finish, I would just like to mention that our paper is going to appear on arXiv in near future. And here I also given references to the two articles mentioned and to some of the figures.